Okay, we are recording. Okay. So we just have well, really only have just one announcement at this time. That's one I've already made over Canvas, but just as a reminder. So class on this Thursday. So here's a little park campus, the classroom there. So those of you here in Hattiesburg, no need to come to a room, just join the WebEx meeting wherever you are. If you want to, you can come here and have the atmosphere. You can see the same thing on the screen, you just won't see me standing right here. So really it's not much different, I guess. Well, except you probably wouldn't be able to hear me as well. So, okay, so hopefully, at least some of you who are enrolled at the Coast can be there. I will be there a few other times on certain Thursdays during the semester, yet to be determined. Okay. I guess I do have one other announcement. I know I have a number of assignments that have been submitted. So last weekend I was away all weekend at a conference. Normally I catch up on grading on the weekend, but I just couldn't that weekend. So what I'll attempt to do this weekend is catch up on whatever I have, whether it's for homework 1 or the quiz or even homework 2. So I'll get there. Okay. So there's going to be assignments due like one after another weekly for a while, and then when we get close to the midterm, then there'll be a gap in homework. So that'll be a chance to catch up. Okay. All right. So I'll be continuing with floating point arithmetic. So last time I what's going on here? Oh, okay. This. Okay, so this is what I covered last time. Okay, so now before I get into today's material, which is some things that can go wrong with floating point arithmetic, one thing I'd like to mention is last time I played around a lot with MATLAB's hex format to see how floating point numbers were represented internally. I know it can be kind of difficult to decipher, but for more information on MATLAB hex format, there's an example in the text. Get the exact reference here. Okay, so in the text, actually it's not a numbered example. On pages 67 and 68, there's a more detailed explanation of the hex format. Also, actually I should share that. Okay, so now I have to unshare and reshare. Okay. Yes, starting here. So when you have these hex digits, hexadecimal represents all numbers from 0 to 15. since we only have digits for 0 to 9, letters A through F are used to represent 10 through 15. So here we have a translation for you, numbers in decimal, hexadecimal, and binary. So you see something like this in hex, that's hex digits, so then you can convert each of these using this table to binary. And then from there you can see, like, okay, what number is represented in the exponent part or the mantissa part. And then here's an example on page 68 that works with a sample number displayed in hex, and how we see what the floating point number is represented. So everything I went through in the various examples from last time, you can see written out more cleanly here. All right. So several things can go wrong with floating point arithmetic. So we'll go over some of those here. A big problem here is that we have limited precision. So in IEEE double precision floating point arithmetic, we only have 53 significant digits in binary that can be stored. So what can happen, but also you can have a wide range of magnitudes. We can have the exponents 2 raised to any exponent from minus 1022 to 1023. So you can have numbers of widely varying magnitudes that you can try to perform operations on, and sometimes the results can be very inaccurate. So I'm going to give an example involving a decimal floating point system that you might find easier to digest, because any floating point system can suffer from these issues. So suppose we have a floating point system in decimal. Hold on. I want to get rid of this WebEx assistant. Okay. So we're in decimal. We have 10 digits that can be stored. And then the exponent range is from minus 20 to plus 20. And now suppose we have two numbers of widely varying magnitudes. So here we have x that's on the order of 10 to the 8th, and then y on the order of 10 to the minus 6. So in other words, 400 million is x, and then 0.0002 is y. So if I were to add these, then this is the exact result. But I'm only allowed 10 digits. So the mantissa cannot hold all of this because I have too many digits. So the effect is that the floating point representation of x plus y is just x. But y, because it is too small relative to x, because y is 14 orders of magnitude smaller than x. That difference in magnitudes is greater than the precision. So y gets lost in the addition. So we see this happen in addition. It also can happen in multiplication and division, because when you're working out the mantissa of a product or a quotient, you're not going to be able to represent those exactly. There are going to be some digits that are lost, just because you have limited space. Whereas if y was larger relative to x, for instance, like y equals, say, 2, so 2 times 10 to the 0, then we would see a digit of 2 here that would make it into a floating point representation. Okay. So, so a rule of thumb here. So the difference in exponents between x and y is larger than the number of digits of precision available, the smaller number will get lost in addition. But so there's no point in adding it because it won't make it to a result. Okay, so. All right. The question about loss of precision. One of the problems. Oh, you know what? Actually, I just realized I need to post the assignment for the section. So I will be sure to do that very quickly after class. But one of the problems that will be assigned is about what if you have a long list of numbers and you want to compute for sum. What's the best way to do that? Keep taking this problem into account. All right. Second issue, that the properties that we take for granted for operations like addition, we cannot take for granted in the floating point system. That we know that in exact arithmetic, addition is associative. So if you add x and y first and then add z, that's the same as adding y and z first and then adding x. But that's not exactly true in floating point arithmetic. That there's going to be some error in these operations, and that can cause these sums to disagree. However, addition is still commutative. So whatever error you incur from adding, performing x plus y, it's not going to make a difference if you do y plus x. The error in that result is going to be the same. One that I've mentioned before, or overflow and underflow. So again, with a sample floating point system in decimal. So here I have, once again, a large number and a small number. So what happens is, suppose I compute y over x. So y is already small, but I divide by a very large number. So y over x is going to be really small. Number 10 to the minus 15. But my range of exponents is from minus 10 to 10. So this number is too small to be represented in this sample floating point system. Now that's not really a big problem. We just declare the result to be 0. So that's a perfectly reasonable solution. But now I compute x over y. X is already large. We divide by a small number, so it's going to get larger. The exponent is going to be 14 now. But that's larger than the largest allowed exponent. This is overflow. So this number is declared to be positive infinity. And you saw when I did something like that in MATLAB last time, I feel like I did 1 over 0. And that's also declared to be infinity. So a system like IEEE has a way of representing infinity in the floating point systems, distinct from ordinary numbers. Now, certain operations can overflow, but maybe the operation can be rearranged so that overflow doesn't occur. And this is one of the problems we're going to assign in this section, 2219. This expression right here, that even if x, the exact values of x, y, and z, can be represented in the floating point system, even if x, y, and z themselves do not overflow. If you evaluate this expression as written, you could still have overflow, even if the final result is okay. So what this problem calls for is to rewrite this expression so you're manipulating it algebraically to get a mathematically equivalent expression that will not incur overflow. And I will say that this is a problem that students in general have difficulty with. So I'm sure I may be giving out hints as we go. So just, you've been warned. But I'd be careful now because I want people to try to make some progress and at least recognizing first what are the circumstances in which something can go wrong? Because that's what you do first. You find out what is the actual problem here, what causes it, and that sets you on the path to figuring out how to fix it. Okay, this next issue is one that I brought up on the first day of class. But the situation happened in the 91 Gulf War, where we have catastrophic cancellation. If you're performing a subtraction, so the x and y already have some error in them because they may have resulted from prior computations. So then you're performing this operation, you're computing x minus y, where x and y are both larger than the exact result, much larger. So here's an example to illustrate why this is a problem. So what happens here is, okay, actually, let me put this onto a new page. Okay, so here we have base 10, and we have 10 digits allowed in the mantissa. So here's x, and here's y. And what we see is that the first 7 digits of x and y agree. Now, because we have 10 digits, then if we assume that numbers are represented by rounding instead of chopping, this is relative error in both x and y in the representation. Okay, so now we go ahead and carry out the subtraction. So when first 7 digits agreeing, we get zeros here. So the result, we only have 3 digits of it. So for relative error in this is going to be 1/2 times okay, it's 3 digits, so it's going to be 1/2 times 10 to the minus 2. So we've lost 7 digits because of the digits that cancel. So the relative error in the result is much greater than the relative error from representing the operands, the numbers that were being subtracted. So this is why it's so catastrophic, that your result can be far less accurate than what you were working with before. So what can be done, in some cases anyway, is to rearrange the computation so that maybe a problematic subtraction can be avoided. And the thing to keep in mind is, it's not all subtractions that are a problem. It's just ones where it's possible for the numbers being subtracted to be very close together and have a result that's much smaller. So if, because of the numbers involved, if you know that's not going to happen, for instance, what if you know that x and y themselves are already small? Then that's not really a big problem. And some computations are rearranged that way, where the new operation looks very similar to the old, but what it's subtracting now is much smaller. So that reduces the cancellation error. Actually, I'm going to give an example of that. Now, this is actually from linear algebra. I'm doing this unplanned, so not sure how well this will go, but. Okay. So suppose we are solving a system of equations. Ax equals b, where A is a matrix and x and b are column vectors. And suppose our method generates a sequence of approximations, x1, x2. And the idea is that the method in question generates a sequence of iterates that converges to the exact solution. All right. And let's suppose that whatever method we're using to generate these approximations relies on a residual. So the residual, which I'll call Rk, which is equal to b minus Axk. Okay. So in other words, suppose we are always computing this at each iteration. Now, because xk, one of our iterates, is converging to x, then the residual is converging to zero vector. So what's happening when we're computing is, b is some non-zero vector that's given. Axk is going to be some non-zero vector. And these two vectors are close to one another. In fact, they're getting closer to one another. So now we're subtracting numbers that are not small and getting a result that is small. So the issue here is that b, or these vectors, they're not approaching zero. So this way of computing the residual, by subtracting these vectors, subject to cancellation error. So this is an example of a problematic subtraction. So here's what we can do instead. So I'm going to make an assumption about how these iterates relate to one another. Suppose that xk plus 1 is equal to xk plus some vector, I'll just call it ek. So whatever the algorithm is doing, it's producing each new iterate as a sum of the old iterate plus some vector that it's coming up with. Then I can do the following. My new residual, Rk plus 1, which is defined to be this, but now I'm going to substitute my representation of that new x in here. But that's going to be b minus Axk minus Ek. But this is a previous residual. So I can write it as Rk minus Ek. Now, we still have subtraction. You might think, well, did we really gain anything? And the answer is yes, because both the vectors in question, Rk and A times Ek, are converging to 0. Okay. So now, yes, the result of this subtraction is again small, but the vectors that are being subtracted are also small. That is what makes the difference. Now, I'm not saying there's no cancellation error, because these vectors are converting to one another. There is going to be some cancellation error, but there's a lot less than with the original computation. So this happens a lot where certain formulas are rearranged in order to that may change bad subtractions into better ones. So questions about what happened here? I'm going to be more precise in my terminology. Less problematic. Like I said, cancellation error is not eliminated entirely. At least not in this case. Now here's a very different example of how to deal with cancellation error. Involving the quadratic formula, something we all take for granted. I'll give an example. Here's our quadratic equation. And the coefficient b in our quadratic is much larger than the product of a and c. So a and c are both equal to 1. And let's suppose that our precision, let's say we're being 4 decimal digit arithmetic, so we only have 4 significant digits allowed. If you were to carry out the quadratic formula, and after each operation rounded to only 4 decimal digits, then here's what would happen. You get one root of 0, and the other root's minus 10,000. But if you substituted both these roots into the quadratic equation, like if you substitute x equals 0, you get 1 equals 0. So 0 is definitely not a root. So that root is not very accurate. Whereas if you substituted x2 equal to minus 10,000, actually, you would again get 1 equals 0. So yeah, so this did not go well.
Both true.
Yeah. Okay, and when I say here both lower roots of problem, I mean from a point of view of subtraction. So, actually, one thing I want to check here. Okay. Okay. I have to be careful about this because, so I haven't discussed here an example, but I should not say how you deal with the problem because that's one of the homework problems. So, sometimes it happens, I accidentally work out a homework problem during class. I've forgotten that I assigned it. So, and I know nobody here would really object to that, but I'm trying to avoid doing that. Okay, so now here we have approximate roots in 8-digit arithmetic. So we see here the roots that were obtained using 4-digit arithmetic were either 0 and minus 10,000. So here, the smaller root is supposed to be minus 0.0001 is better approximation. And the thing is, this number, minus 0.0001, can be represented in this 4-digit floating point system because there's only one significant digit, and so using a quadratic formula as written on this equation, this a, b, and c, gave a root that is not accurate, even within the limited floating point system that you have. On the other hand, this root right here, if you took this number and want to represent it in a 4-digit system using rounding, you would get minus 10,000. So in terms of the limited precision that you have, this is the most accurate root you can get in 4 digits, 4-digit arithmetic, because it accurately represents this with the limited precision that you have. but this does not. So even though you get something pretty bad when you substitute it into the equation, in terms of actual error, like a relative error between this root and this one, as opposed to this root versus this one, what happens here is the relative error in this root, when compared to this one, the relative error is 1. So that's horrible. Whereas the relative error in this root, in comparison to this one, is actually quite low. That's why I have a statement of notes. At most, one of the roots is problematic. Because what happens here is, here are your two solutions. And depending on the values of A, B, and C, one of these roots will have a problematic subtraction, but only one of them. So this problem is about algebraically manipulating a quadratic formula to not perform that bad subtraction. So I'd be careful not to say anything more about that. But yeah, so what you get is a new quadratic formula. So if you're running like a MATLAB function whose job was to compute the roots of a quadratic, you would use both the original quadratic formula and the modified one. So each formula would be used to compute one of the roots in a safe manner that does not have a bad subtraction. Questions about this one? Here's one I did not assign as homework. So, oh wow, I'm going to my notes. So since I did not assign this homework, I can work it out fully. So this expression, 1 minus cosine x. And we're going to assume that x is nearly 0. So in that case, cosine x is nearly 1. So now we have two non-zero numbers that we're subtracting that are close to each other. And so the result is going to be nearly 0. So this is a bad subtraction. So you can use a trig identity. So if I use this half-angle formula for sine squared x, what I can do is I can write 1 minus cosine x as 2 sine squared x over 2. So this doesn't have a subtraction at all. At least, except for whatever you do to evaluate sine, because evaluating sine in hardware is going to perform arithmetic operations. But here, as long as sine of x over 2 is evaluated accurately, then this expression will also be evaluated accurately. So sometimes relationships like that, trigonometric identities, can be used to rearrange an expression so that it's mathematically equivalent, but from a floating point arithmetic standpoint, works much more nicely. Here's another example. Okay, so if I use a approximate of sine x using a difference quotient, so that'd be sine x plus h minus sine x all over h. So this will incur cancellation error if h is very small, because you have these values that are generally not going to be close to 0, but their difference will be close to 0 if h is small. And whatever error you get from this subtraction will be amplified by dividing by h. We solved that last time. So, what you can do is so some product formula. This is another trig identity. Sine A minus sine B equal to 2 sine, and let's make sure we get this right. Okay. I think this one is okay. Now, I may have this wrong, but okay. So, okay. If not, it's close. So, if I have the right side of this, okay, so I have sine A is equal to the same as oh, that should be A plus B over 2. All right, so this is a way of writing A, because the B over 2 and the minus B over 2 will cancel. But if I use a trig identity for the sign of the sum, that's going to be A plus B over 2 cosine minus B over 2. Okay. Whoops, I forgot to make it bigger. Okay. Plus cosine sine. Okay. All right. So this is a way of writing sine of A. And I can do the same thing with sine of B. That would be the same as sine. Okay. A plus B over 2 minus A minus B over 2. Okay. Because if I add these two together, I will get B. And that's going to give me the same expression except for the sign in between. Where'd it go? It's minus. Okay. Oh. Something went wrong here with copy and paste.
Yes. It's too much. Yeah. Yes.
Okay. So now if I do sine A minus sine B, these cancel, and then these will add together. Cosine A plus B. Yes, so this is correct. So that was the result of all that. Okay. So now if I apply that to sine x plus h minus sine of x, okay. So all I have to do here is use this formula with A equal to x plus h and B just equal to x. So that turns out to be 2 sine h over 2 times cosine of x plus h over 2. Okay. So here we don't have subtraction to deal with anymore. And I can divide both sides by h. Okay. Now what's interesting here is, as h gets smaller and smaller, sine h over 2 converges, this fraction converges to 1. Because for small arguments, sine x is approximately x. So the limit of this as h goes to 0 is 1. And then the limit of this as h goes to 0 is cosine of x, which is a derivative. So in terms of floating point arithmetic, this would work more effectively than the original. So the questions about this rewriting to get rid of the cancellation error. So it's good to know your trig identities. Unfortunately, most students only remember sine squared plus cosine squared is equal to 1. One of my colleagues actually said that really the only trig identities you need to know are the ones for that one, but also ones for sine or cosine of a sum or difference, because from those you can derive so many others. Now, what I'm going to attempt to do, and keep in mind I've not done this, this is again impromptu. I want to try these formulas out in MATLAB. Like I'll pick a value of x and h small, and go ahead and compute these and see how they compare. So I'll pick x equal to 1, h equal to, say, 10 to the minus 5. Okay. So the first expression is the sine x plus h minus sine x all over h. Now we'll see it in format long. Okay, so what I want to find out is there a significant difference, at least for these values of x and h? At what point can we actually see cancellation error? So expression 2 is going to be 2 over h times sine of h over 2 times cosine of x plus h over 2. Okay. They agree up until these last 4 digits. Okay. So we do see some cancellation error there. So now let's make h smaller and do the same thing. So expression 1. Okay. All right, not as much agreement. And we keep in mind the true value of a derivative, cosine of 1. Let's take a look at that. Okay, I'll call that the exact derivative. Okay. Notice it agrees much more closely with the second one. So let's look at the relative error. The relative error in the second expression, which is the one that doesn't have cancellation, yeah, that's quite accurate. But the other expression that does have cancellation, oops, sorry. So we can see that as a finite difference approximation, this is what the error can be given the value of h. You're going to have some error because it's only an approximation. You're not taking the limit as h goes to 0. But the actual error you get from using the finite difference formula as written turns out to be this. And the thing is, for a function like sine or cosine, or maybe other trig functions, we can rewrite these difference quotients using trig identities in a way that it can be evaluated more accurately. But what if you have some other function? Maybe you're not able to do that. So these finite difference formulas generally are used the way they're written because they need to be used for a general function. but they can have these problems if h is chosen too small. Okay. So questions about what happened here about cancellation in general? I apologize for not having a break. This is the view of a late start and a knowledge that whatever material I had to cover was not going to fill the time. So, but in any case, but yeah, I've come to the end of section 2.2. So coming up next, we're actually going to jump to chapter 7. I know it seems like a big jump, but we're not. We're skipping over numerical linear algebra because that's for another course, and we'll deal with polynomial interpolation. So working with polynomials is relatively harmless. They're such nice functions, but we certainly have time for any homework questions. Over on not everybody has turned in homework 1. Actually, okay. No, not even a majority. Well, actually, it is. Yeah, just barely. Well, half a class would be 11.5 students. Just over half have turned in homework 1. More people have turned in the quiz. Okay, and so we've gotten the next quiz in. That's good. Okay, so if you are still having difficulty, I urge you to, you don't want to ask questions in here, that's fine, I understand. Or you can contact me outside of class, or shoot me an email. Okay, so, but does anyone have any homework or quiz questions? Oh, I think there's something in the chat. Okay. 2.1.13. Okay. Okay. So the idea here is to use the approach from the example to arrive at this error formula for this forward difference, and this error formula for center difference. So the way that is done is, well, let's review the previous example, what was done with the second derivative that involved the same expressions, f of x naught plus h, f of x naught minus h. Whenever you're evaluating f at a point other than x naught, so here and here, you use these Taylor expansions. And in fact, the one shown here, written like this. Actually, I think for a problem, this is the only one you need. You only have a. Let me check. Oh no, you need both of these. So you can use these that they have a sufficient number of terms in them. Okay. That you can substitute the Taylor expansions here, here, and here, and then simplify as much as you can. So you'll have several terms cancel out. Not to mention simplifying from dividing by h, and the first term that you get that does not cancel will be what you're trying to compute. In this case, it's f prime of x naught. The next term after that is going to be the error term. Hold on a second. Now, actually, I will give a little extra hint for this first one. Because one issue is, when you take a Taylor expansion, here I've taken it out to h to the 4 for the example. How far out do you need to go? Okay, so just like if you look at what was done in the example, this is the error term. So the and the leading term in the error is the one that was where the derivatives are evaluated these unknown points. That's the remainder term in Taylor expansion. So the term that's going to be the error term, you want that to be the remainder. Okay. So the question asked in the chat is: you expand to 1 degree higher than the error term? That's one too far. So make sure that the error term comes from remainder term. So what that will mean is that actually both of these Taylor expansions, while they're perfectly fine for the example, they both go a little too far for these right here. Now it's better to go too far but not far enough, because at least you can see everything is going to cancel. Because sometimes due to symmetry, certain terms will cancel out. But if you have an expansion like this one that's too many terms, at least you can see what's going to cancel and what isn't. And then once you see what is after your approximation, you have prime of x naught, when you're trying to compute after that falls out, the next non-zero term, that's the error. So that's how far you go. So I think I'm going to put this in the notes.
So any non-zero, once you get your first non-zero term, use that as your what do you call it, remainder.
Yeah. Okay. So so after you cancel everything you can, f prime x naught will show up. The first non-zero term after that, that's the error. Make it the remainder. Now, the first one will be a little bit easier because you only have one Taylor expansion. So when you get to this point where you have identified the error term, in the first finite difference formula, there's only going to be one term. So you can essentially stop there, that's your error. For the second one, you'll have two Taylor expansions. So you're going to have parts of the error term come from each expansion, but that is exactly the same situation as what happened here. So you're going to use the same approach where here you have a sum of some derivative of f at two different unknown points, but then it's possible using the intermediate value theorem to basically to combine them into one. But notice how I wrote it. When these were added, I have 1/24. But I wrote it as 1/12 times 1/2. What I have here is an average. So the intermediate value theorem says that if a function is continuous on an interval AB, then there's some point in the interval where a function is equal to the average of the values at the endpoints. So there's some point between C1 and C2 where the fourth derivative of f is equal to the average of those values. So if you look at what happened from this step to this step, notice the minus 1/12 is still there, the h squared is still there, but this expression, 1/2 at fourth at this point, at fourth derivative at this point, got replaced by the value of fourth derivative at a single point. That's the intermediate value theorem at play. So the exact same argument can be used in this case. So I've included the error terms here so that you can verify that this is what you get. So you'll know if you got the right result or not, like making sure you have the right constant factors so that you have the right error. And whatever power of h you have, that's the rate of convergence of the error to 0. So this one is order h, this one is order h squared. So I don't know if that answered your question. Okay. Any other? Still have time.
Professor, I have a question concerning the linear algebra example.
Okay.
So you convert the residual RK to the bottom one, and both RK and ADK converging to 0.
Yeah.
But the sequence is Cauchy, right? So Cauchy sequence, they will also, very close to each other when they goes to infinity.
Right.
So subtraction of two close numbers still occurs.
Well, yeah, that's why I say cancellation error is not eliminated entirely.
Yes.
It is reduced, and the reason why is because at least these are getting smaller,
Yes.
whereas when you compute residual this way, all that's happening here is they're getting closer together.
Yes, the left-hand side one is more closer than
Yes.
than the right-hand side one.
Yeah, so that's why I hedged a little bit. This subtraction is less problematic.
Okay.
Yeah.
And another question, Professor, can you explain more about how to convert a decimal number to a float point number?
Okay, so in other words, you're saying if I have a given number decimal,
Yes.
how I get into like IEEE?
Yes, IEEE 754 standard, right?
Right.
Yes. So how to convert it to float?
Okay. All right. So. Okay. All right. So we can make up a number here. Literally just random keystrokes gave me this number. Okay. So the first thing to do is get a handle on its magnitude in terms of powers of 2. All right, so the exponent.
9.
Okay. Oh wait.
Let's take floor.
Okay. So if I go to MATLAB. Okay, yeah, so the log is 9.8, so I round that down to the nearest integer, so the exponent is 9. Okay, now, the number stored, though, is the exponent plus 1023. Because in order to determine what bits are stored in the exponent part, But now that has to be converted to binary. So 1032 is going to be equal to, if I break it down to powers of 2, that's equal to 1024 plus 8. So in binary, that's going to be, I'll explain how I get this in a moment. All right, so 10 times 8, 6, 5, 4, 3, 2, 1, 0. So the 1024 is 2 to the 10. Whoops. Plus 2 cubed. Okay. So that's why we have 1s in the 4th and 11th positions from the left. So this gets actually stored within the 64 bits in the exponent part. Okay. So the start of the hex tool. So the start of binary representation would be equal to the first 12 binary digits would be 0. 1,
Positive.
10, 9, 5, 4, 3, 2, 1, 0. Now, if I group those in groups of 4, okay. As far as hex digits are concerned, this is 8, and then 0, and this is also 8. So these are the first 3 hex digits that describe this number. That accounts for this first 0 here is a sign bit because it's positive. And then the other 11 binary bits come from the corrected exponent or adjusted exponent. Now what's left is the mantissa.
Yes.
So the 52 remaining binary bits. And that's a bit of a pain. What I need to do is, so the actual value of mantissa is the x divided by 2 to the exponent. So I need to divide 2 to the 9th. So that's always going to be a number between 1 and 2. So 1.75. Okay. So now I have to convert this to binary to get the digits of the mantissa. Now, the first digit is a 1 because it's 1. That's right here. Then we do this repeated procedure of subtract it off. Now I have everything else.
And times 2.
Yes. What's this? Okay. Then multiplied by base. All right. So that's 1. That's 2. And I get this. Okay. And we see that we have a 1 to the left of the decimal point. And then we just keep going. And what I'd like to do here is at least get 4 of the digits. Okay, so because then that will give you the next hex digit. Okay, so then take. All right, so now I have that. So then my third digit is again a 1. Okay. But now what we see here is after we subtract the 1 off, it just depends on what the number is, how it works out. We're going to get something really small. So now we get something that is much smaller than 1. So the fourth digit is 0. So the first 4 digits of the mantissa are 1, 1, 1, 0. Although this 1 that was here to begin with is not stored. Yeah. So what would happen is if I subtract, doesn't change anything. So I'm subtracting 0. Whatever digits to the left of the decimal point, that's what you subtract. So nothing changed. And then multiplied by base. And I get this. And the next digit will again be 0. Okay. So far, this is 1.1100. Yeah. So now the next hex digit comes from the 4 digits that follow the binary point. So this is 8 4 12, so ABC. That's 12 in decimal, which is C in hex. So now if I take the number that I started with, all right, so I have that here, and I look at it in hex. Oh, I think I screwed up somewhere. Oh, I did. Oh, okay. Oh, I see. Okay, I messed up. 0, 1, 0, 0 in binary is 4, not 8. Okay, so now I have 408. So that accounts for the sign bit and the exponent. And then the first part of mantissa is C, which is what I got here. Okay. So then I would keep going. That would take a long time to get the rest of these.
Oh, I see.
Yeah.
Thank you.
Nothing to it. Well, you could write a bad program to do it, I guess.
Yes.
So why is the first digit not stored?
Sorry, what? Oh, because when it's binary, the mantissa is normalized, so it has to be
Always 1.
a non-zero digit to the left of the decimal point. But when it's binary, the only choice of a non-zero digit is 1. You know what it is, so don't store it. But if this was different base, you'd have to. Okay. All right. Well, we have to answer the last time, but I'll stick around for any other questions anybody has.